Yo, what's up, everyone? First, check me out. I finally got a printer and it came in the mail, set it up, and I will be able to print out the worksheets from now on. So I'm really stoked about that because it's easier for me, and this makes me feel really comfortable. It's nice to see a worksheet out, and we're at it with week 3, and so far, honestly, I gotta say, Algebra 2, we're crushing it. So I'm really proud of what we've done, and this week it continues to get good, it continues to get better, and continues to be mostly review. So I'm assuming, at least for this first unit, that you've seen all this stuff before, but we're going to do it again because a lot of the structures are similar later in the year, and it's also really important. This is fundamental algebra. So before you graph it, if you go to add arrows here, I actually struggled to find the arrow thing, but add arrows for all the graphs that you see that aren't word problems. Okay, and there's only going to be one practice word problem, but I want you to put the arrows in here. And it says for us to write the piecewise function for the graph below. Now, here is what's happening. Last week, the week before, we were talking about lines and graphing lines, and we know that a line has a constant rate of change and is unending, right? It goes from one side of a graph all the way to the other. But here, there's changes, right? And the key to these changes is that our graph is split up into 3 parts, and each part is actually something we could write. So think that the graph is a line until it hits this point. So we could say that this is section 1 of my graph. Then it becomes a straight line here, and that's a different line here, and then finally it goes up again here. And this line, therefore, is 3 lines in one. Okay? So our strategy for writing this is we're going to basically do them separately. And we'll start with just figuring out the equation for this line, and then we'll talk about the entire notation. So what you notice with all of these actually is, like, look, there's like no A, B, C, D. There's only one thing. We just have to write this equation. So if I'm trying to ever find the equation for a line, I'm trying to find the slope. And if I want to find the slope, I pick 2 points and I figure out the distance between them. Okay? So we're going to use the slope formula. We can use the slope formula here, right? But know that as I move over 1, we're only going up half a box. So this slope is going to be a fraction. So maybe here, for this first section, it would be best if we just use the slope formula. So we could say that this first point is -2, -5. The second point is 0, -4. And we're going to find the slope. y2 minus y1. And hopefully everyone's on the same page as me. So all I'm doing right now is I'm going to try to find this part of my line, and what would that equation be? Okay, so I'm going to find the slope, and then I'm going to find the y-intercept, so we can put it in y = mx plus b form. So here, it's -4 minus -5. So that's going to be 1. And 0 minus -2 is 2. So the slope is 1/2. And again, I usually shortcut, but think that as y goes up 1, so the change in y is 1, x is changing 2. And the y-intercept is wherever we touch this line, right? So if I touch this line at -4, this is the y-intercept. We can use this to write our first equation, and that's in y = mx plus b. So y equals 1/2 x minus 4. So let's do this for all of them. And we'll call this 1 for now, because we have to do the other 2 also. So for 2, this line is going straight. And we haven't talked about this yet, but it's pretty easy. Think that there's no slope here, right? The line isn't going up or down at all. It's constant. So the slope is 0. And all we have to figure out is what the y-intercept would be if this line kept going. So this line is always at -3 for y. So the equation we write for that is y equals -3. Okay? So vertical lines, which we'll talk about eventually, but it's a little different, it would be x equals a number. But think a straight line is that line is at -3. So it's y equals -3. And now finally we have to find this third equation. What's happening from here to here? And we'll approach it the same way we found the first one, with the slope, but the slope is a little easier to read. I'm sweating. That's disgusting. It's just so hot. You guys know how hot it's been. Oh my god. Okay, so if we're going from here to here, think that the change in x was 4, or sorry, the change in y was 4, and the change in x was 1. So the slope here is 4. We're going up 4 for every 1 move in y. So the slope equals 4, but what's harder here is the y-intercept. Okay, so you could continue sketching until you find it, but let's think what is a second solution, or second way, that we can find the y-intercept. And that's by plugging in a point into the equation. So I know some of it seems like a lot, but hopefully we're just crushing it with our line skills. But here, we know the slope is 4. And if I want to find that part of the equation, I'm going to plug in a point. So this point is 5, -3. So let's plug in 5, -3. X was 5, y was -3. 4 times 5 is 20. And I realize I didn't give you enough room, potentially. But here we get a really big number, but it doesn't matter too much. We get -23, and that makes sense, because if this kept going, it'd be way off the graph, and the y-intercept would be -3. So for this third section of our graph, the equation is going to be 4x minus 23. Okay, so this is the part that's a little bit harder, but I don't think it's too bad. So we're trying to write the equation. We have 3 equations, and we just know this is what y equals. Y equals this sometimes, y equals this sometimes, and y equals this sometimes. So we're going to write y equals, and then I want you to use this kind of caret parenthesis. This is just a notation, and I want you to write your 3 equations. Okay, so we know that sometimes it's this, sometimes it's this, and sometimes it's that. The 3 equations. And once we do that, all we have to do is figure out where exactly it happens. Okay, so my first section starts here, right, forever that way, and stops once we hit this point, right? So it's from here all the way this way. Think this goes forever, so -infinity, all the way until we hit, no, I messed it up. This point. So section 1 goes from -infinity all the way until 2, if we're talking about the x values. Okay, so we're trying to write where this goes from. And because this line extends forever, think that this graph goes from -infinity all the way to 2 before it changes. It's this equation for all of that. So write a comma, and that's going to be basically when. And for now, don't worry about the less than equal to sign. but think that once we hit this point, we're still that. But so basically, yeah, from negative infinity to 2, we're this equation. Now we're going to write in this is called interval notation. Okay, so we can actually close out the parenthesis to see what's happening. This is going to be the entire equation, and we write the equation and when it happens. So when is it negative 3? It's negative 3 from this point to this point, right? So from 2 to 5. So we can just write from 2 to 5. And then finally, the last section starts at 5. Okay, so these are going to be continuous always, right? Or at least for now. And then it goes on forever. Think that this graph goes forever in both directions. It starts with 1/2 x minus 4, then it becomes negative 3, and then it becomes 4x minus 23. So that was a lot of work, but the good news is you'll get even better at drawing lines. So the beginning of the unit will seem like a joke once we get to the test, but that's going to be how we write the equation. Okay? The second example, hopefully this now makes everything feel a lot better. Okay, so for number 2, we're going to go backwards and basically think that you've already learned pretty much everything. So now we have it in that funky notation, and we want to turn it into a graph. Okay, so think here that these are where it's happening. This first equation is happening on the left side all the way until we get to 0. This second equation is from here to here, and this third equation is from here to here. So first, let's draw 4x plus 4. We know it's this entire direction, all the way to the left. And if we ever have to graph an equation, remember, let's use slope and y-intercept. So both in this case are 4. So if I'm trying to graph that first equation, we're going to start at 4. And it's going this way, right? So our graph is going up as we go to the right. So think that it's going down to the left. So the slope is 4. So that is what the graph looks like. Okay, and it keeps going forever. Okay, so now you kind of get it. Like when you're doing a piecewise, you're pretty much just doing 3 equations, and the hardest part here is going to figure out where they happen. So from negative infinity all the way to 0, on the x is the first equation. The second one is just going to be here to here, and it's telling us that it's negative 7 over 2 of x plus 4. So we can do the same thing. The slope is negative 7 over 2. The y-intercept is also 4. So the point is the same, right? But from here to get to the next point, this is our slope. And if we have a fraction slope, remember that that's actually really easy. Think that the top is changing y. So y is going to go, and we can put the negative on the top. Y is going to go down 7. 1, 2, 3, 4, 5. Let me write this way. I don't know. 1, 2, 3, 4, 5, 6, 7. And then x is changing 2. So that's what that would look like. Okay? And it just so happens that we're going 0 to 2, so this works really well. But think that if you just see 4, you're changing x 1. But if you have a fraction, you change that bottom's amount. Not perfect, but I'm over it. That's fine. And then we're going to do this final one. So it says negative 3. Oh, there's a typo here. Negative 3 from 2 to infinity. So remember, if you just have a number, think there's no slope. There's no x here. It's going to be a straight line. And that straight line is occurring at negative 3. So that's what that would look like. Okay, so far pretty painless. This last example might be a little tricky, but that's really that, and that's the fundamental skill. So piecewise is really just a bunch of functions on the same graph. Okay, so here's our last example, and I'm pretty happy with this because this is the whole reason why we do piecewise functions, right? So think about the word problems we did last week, and how a lot of times when you are trying to model something, it's not just going to be a straight line that doesn't change, right? A lot of times, if you're talking about money, for example, the rate of change changes, and stuff like that. Okay, so let's read the question. It says, imagine you're using a taxi in New York City, and the taxi costs $5 for the first 4 miles. And after that, the meter starts running, and the taxi costs 50 cents for the next 16 miles. After that first 20 miles, the taxi costs 25 cents. Okay, so we're trying to graph this word problem, which is why we don't have the traditional axes. And if you're ever trying to graph a word problem, figure out x and figure out y. So remember that x is the independent variable, and y depends on whatever happens to x. So here your taxi costs more money the farther you go. So x is going to be miles of journey. And y is going to be the cost. Okay, and cost is a pretty classic y, right? Because you do something and it costs a certain amount of money depending on what you do. In this case, how many miles you drive. So think here that the bottom is miles, okay? And as we go up, it's cost. So think what happens when you start driving. We can make this by 2's. So 4, 8, 12, 16, 20, 24, etc. So the scale you always kind of choose on your own. But think for the first 4 miles, how much does it cost? And we know that it starts at $5. Okay, so when we're going this way, some of the numbers are small. So let's honestly just go by ones. Okay, and hopefully we don't go off the graph. We're going by ones here. So think for the first 4 miles, it costs $5. Then the cost starts going up from here to here until we get to 20. For these 16 miles, the rate of change is 50 cents per mile. And what can be hard here is when you have different scales. So this way we're going 2, and this way we're going 1. So we know as you go from here to here, we're going 2 miles, and if we go 2 miles, our cost is going to go up $1. Right? So actually, it's going to look like this. And the scales we chose were perfect. It's trial and error practice, but think that you're going to move up $1 every 2 miles. So that's what the graph looks like. And some of you might already be set. Some of you might already get it all, like how you're going to make your Okay, so that's part 2. And think that we're going to make this equation. So this is part 1 of the piecewise, this is part 2. And then after 20, it's 25 cents. So think that it's going to start costing less. It's going to start going up less often. It costs half as much. So that would be, in theory, to infinity if you drove the taxi forever. So that's our equation, and hopefully that makes sense to everyone. As what happens when you use a taxi, right? If you use it for a long time, they don't want it to be an insane cost, so it starts to go less and less. So that's our graph, and now it's telling us to write the equation. Okay, so the equations here might be a little harder, but you can do this either way. Sometimes I just like to write my intervals first. So the first, this is terrible, whatever. The first interval is from 0 to 4, right? The first 4 miles. And we'll put the equation there. The second one is from 4 to 20. And then from 20, kind of to infinity, okay? We'll just say infinity. Because it doesn't give us a specified end, like it doesn't say there's a maximum. So those are our 3 parts, and now we want to write the equation. We start with a straight line, so that's good. We know that at first, it's just equal to 5. This second part we're going to rely on the word problem of what it tells us, right? The rate of change is 50 cents per mile. And right now we're trying to find the slope. So every mile, y goes up 50 cents or 1/2. So the slope here is going to be 1/2. We can actually just plug in our slope for the second part now too. Think that the slope is eventually going to be 1/4. But we got to figure out what is that y-intercept for this line. And in this case, you actually could go this way to figure out that it's going to be 1. But let's use the plug-in point method. Okay, so we have part 2 and part 3. Here we know it's y equals 1/2 x plus b for trying to figure out b. And for part 3, the slope is now 1/4, and we're trying to find b as well. So let's plug in a simple point on this 5, 4. Sorry, this point is 6, 4. So I'm trying to figure out this part of the equation. So this point, 6, 4, plug it in, 4 equals 6, 3 plus b. b equals 1. I'm going a little fast through stuff I've done a few times, but we figured out that equation. Y equals 1/2 x plus 1. So that's going to go here. And we can do the same thing for the last part of it. And let's plug in this point. So 20, 11. So this is 5, 20 divided by 4. So we're looking at 6 here. Okay, so this is b, but this is the equation. So that timed really well, and I think it wasn't too bad on material, but we're going to talk about word problems a lot next time. So this time really kind of just focus on the basics. But we crushed it today. Really, really nice job. Woo!